Okay, here we are in the Turner Quad on SMU campus. Again, we're looking at the world through a mathematical lens. And we're standing in front of the Cooper Centennial Fountain behind me. And I want you to take a look at the cascades from that fountain and see if you notice anything that's sort of interesting about what you see about how the water is falling. Now, there's lots of interesting things you might notice. For example, you might have noticed that the water seems to form a kind of a sheet or a curtain as it falls. But you may also have noticed that the width of that sheet decreases as the water falls. So in other words, the sheet actually seems to get thinner from side to side as it goes down. Why in the world would it be that way? Why wouldn't the water just fall straight down? After all, it's coming along a channel that's straight, and the sides of that channel are straight. Why wouldn't the water simply fall straight down, making a rectangular sheet instead of the sheet that gets narrower as it falls? Turns out there's a really simple mathematical explanation that shows why it has to fall that way. And it all has to do with the amount of water that's falling past a certain place in a certain amount of time. So if I make a sort of schematic diagram of that water falling, I want you to think about any horizontal line. Could be up here, could be down here. Think about how much water is flowing past that line in a given amount of time. If you think about it, the total amount of water that goes past, so we'll call that the flow, has to be equal to, well, how much water there is in a given instant, which is the width of that flow, times how fast that water is falling, the speed of that water. So the flow is equal to the speed times the width. A very simple relationship. It's very clear. That tells us how much water. So the amount of water flowing past here is the width there times the speed it's flowing there. Or right here, same thing. The width times the speed it's falling past that line. All right, well, what does that mean? Imagine that the width were constant. If the width were constant, there would be a linear relationship between flow and speed. Flow would be speed times a constant, if that width were a constant. Well, what would that mean? Well, water, like anything else that you throw over the side of something, speeds up as it falls, right? We know gravity acts on the water and speeds it up as it falls. That means the water down here is falling faster than the water up here because it's been falling for longer, so it's sped up. Well, if the width were constant, that would mean there'd be more flow across this line than across this line. But where does the water come from to flow across this line? It comes from up here. So there can't possibly be more water down here than there is up here. It's the same water, just a second later. So the amount of water has to stay the same. The fountain doesn't magically create water from nowhere. So the width can't be constant, because then we'd have to have magically more water here because it's moving faster. So the mathematics tells us that the width has to decrease because the speed increased because the same amount of water flowing at every level in the fountain. So mathematics tells us why that stream has to narrow as it goes down. And this is great because this is an experiment you can do at home. Turn on your tap to a low level so that the water is flowing out nice and smoothly, and you'll be able to see that the width of that stream near the top, right near the mouth of the faucet, is wider than farther down. Anytime there's a stream of falling water, it always narrows as it goes down because the same water is going faster, and so the width has to decrease. Now, you might wonder, what about the two outside fountains? If you take a look at those, they don't really seem to decrease, but if you look closely, they do decrease, just not as much, and that's because the level of the water there is thicker. There's a lot more water coming out of those fountains, and so it doesn't need to decrease as much to compensate for the increase in speed because there's also a lot of width there.